Pretty much did. I mean, I ran you through a couple of examples of problems, the ways to think about this. I'll just show you a couple more things here. There's really nothing really to show you. We did this in lab. Here's an experiment where we considered heat as either a reactant or a product in your reaction as well. And you can use Le Chatelier's principle in the same way. I think this was the one similar to the one that we did in lab. In fact, it wasn't quite this one. But in the one we did in lab, it was exothermic. Heat was a product, right? Heat as a product. Meaning that it's exothermic. And the other clue that things are hexothermic is if you're given delta H and it's negative. When delta H is less than 0, negative, that's also what we use for exothermic. It's not negative energy, right? It's just the negative sign is just the flow of energy coming out of the system into the surroundings. Okay? So in this case, if we know that it's an exothermic reaction, and you can see it, it's kind of listed for you down here in the table, where once again it's displaying. That's so weird. If we were to heat this up, which direction would this reaction go? If we add heat to an exothermic reaction, is it going to shift to the left to form more reactants, or is it going to shift to the right to form more products? This way, right? Because we're adding more of the product. So Le Chatelier's principle, that's the stress on the system. It's going to reestablish a new equilibrium by shifting things to the left, because think of it like a teeter-totter, right? We're adding more things on the right-hand side, so it's going to shift to the left to compensate. The same is true with heat, all right? If we add heat to this reaction, it's going to shift to the left. If we remove heat by cooling it, now we're taking away a product, so the reaction is going to shift to the right. This is exactly what you should have described in lab last week. Not all of you did. All right, some of you still got confused by it. So that's why I wanted to emphasize this once again. And here you can even see the logic written out for you here. And just to remind you, all right, if it's endothermic, that means the heat is absorbed by the reaction, and delta H is positive, okay? And if it's exothermic, heat is produced, and delta H is negative. Okay? We talked about catalysts last time. We can talk about catalysts again now with respect to equilibrium. So here's a graph that should look somewhat familiar to you. Where in blue, we have the uncatalyzed reaction, and you can see the activation energy. We have a regular reaction coordinate, progress of the reaction. I call this the reaction coordinate. All reactants, all products, activation energy, and what's at the top? This is good review for chapter 13 as well. What's at the top here that I used the double dagger for? The transition state. Transition. That's not how you spell transition. You have to remember what that transition state is. It's something that's really, really unstable. Right? It probably has more bonds than it normally could have if you were to try to draw a Lewis structure for it. All right? It requires a lot of energy for it to even exist. But once it's made, it can resolve either in the forward direction to make products, or it resolves in the reverse direction and goes back and remakes the reactants. But either way, it takes a certain amount of energy to get to the transition state because it's unstable. Anything that's unstable can be stabilized if you give it enough energy. That's what we're calling the activation energy. And we know what a catalyst does, right? A catalyst will increase the rate of the reaction by stabilizing the transition state. So catalyst increases the reaction rate by stabilizing the transition state, or the transition complex, or the, what's the other word we use for those? Activated complexes, yeah. There's a whole bunch of activated complexes all leading up to the magical transition state. So it does this by lowering the activation energy. And you can see, here's the lower activation energy for the catalyzed reaction. How come the peak for activation energy happens earlier in the progress of the reaction than the uncatalyzed form? That has everything to do with the mechanism of the catalyzed reaction, all right? Yes, we're using a catalyst, but the mechanism is also different. In fact, you can even see this as sort of a two-part mechanism, perhaps. If you go back to the slides in chapter 13, where I showed you an example of that with ozone being depleted, going back to molecular oxygen, and you add a catalyst. You add a catalyst to that, it goes faster, but that turns it into a two-step process. So in that two-step process, right, the first one, the slowest state, the slowest step, just happens a little bit earlier in the progress of the reaction.
To make different concentrations at the same K.
So are they changing KEQ, or is it just changing the concentrations, or what is it doing? Okay, that's an excellent question, all right? Now, when you take a look at this reaction, all right, we can see activation energy is changing, okay? What's not changing when we add a catalyst here? What? It's not concentrations.
Energy for reactants and products.
The what?
Energy for reactants and products.
The energy of the reactants and the products. Here, I need a different color for that. Let's use green. All right? The initial and the final energy, whatever that energy is, if it's free energy, or it could be enthalpy, or it could be anything. Final minus initial. The change in energy is the same. And why is it the same? It's a state function. All right? We learned this when we talked about catalysts as well. So what we're doing with the catalyst is we may be increasing the rate of the reaction, okay? But what are we doing? What does that mean with respect to equilibrium? So catalysts change the rate of the reactions. We learned that in chapter 13. But what does it do with respect to the change in energy? Here, let's call it free energy so you can even recognize what's happening here. Let's call that delta G, and let's call this free energy. Okay? What's it doing to delta G? Is the catalyst changing delta G? No. It's a state function. Does not change delta G. Okay, so we get to equilibrium faster but KEQ is the same. This doesn't change, KEQ doesn't change. All we're changing is the rates. But remember that rate, how fast you get there. Equilibrium describes what it looks like when you're there. All right, are we clear on that? Don't get fooled. Here, let's even put this equation up here for you. Delta G naught is equal to minus RT times the natural log of KEQ. Okay? We do get to equilibrium faster, okay? But that's it.
Like in the last slide, it said that temperature changes.
Yes, it does. I didn't want to get too much into temperature. All right, temperature will change things. All right, temperature is part of this equation. I'm trying to stick to examples where temperature is not a factor in here. Temperature absolutely does factor in. If you want, I can pull up the Arrhenius equation again, where there's temperature in that, and we can look at that. But I don't think we're going to get into that. So what do you already know about this reaction? Just look at the KEQ. Is this products favored or reactants favored? It's products favored because K is huge, right? So the products on the numerator are much, much larger than the partial pressures of the reactants. So this is products favored. You can tell just from the exponent. All right, so what are we going to do? We're going to calculate for the decomposition of NO2. Now, where is NO2 in this reaction as written? Is it a product or is it a reactant? It's a product. So this reaction describes the decomposition of NO2 or the formation of NO2? The formation. We're asked for the KEQ for the decomposition. So we need to look at this in reverse, and we only want it for 1 mole of NO2. Let me specify that. 1 mole. But our formation reaction is for 2 moles. So we need to do some of these manipulations. So first, let's run it in reverse, okay? Or we can cut it in half. Which one you want to do first? All right, let's just cut it in half. So step 1, let's cut everything in half. So that's going to be NO gas plus 1/2 O2 gas goes to NO1 NO2 gas. So what's the K going to be for this? So K 1/2. What's that going to be? You have to go back and think about the rules. We're cutting it in half, so we raise it to the exponent of whatever factor we scaled this reaction by. And that factor is 1/2. So that's going to be equal to K sub P, the square root of it. Right? So that's the square root of 2.4 times 10 to the 12th. So 2.4, about 1.55, that makes good sense. So 1.55 times 10 to the 6th. So that's the new KEQ running this in half, cutting it in half. But now we need to run it backwards because now we need to run it in reverse. So now we want NO2 goes to NO. Here, let's be careful here. States of matter goes to NO plus 1/2 O2 because this is the decomposition of 1 mole. That's what we're doing right here. Finally. Here, let's put both of these go into this. All right, so now we've got K 1/2 in reverse. What's it going to be? You have to go back and look at your rules. Right? Forward and backward Ks are related by what? They're inverse. So this is going to be the inverse. It's going to be 1 over 1.55 times 10 to the 6th, which is 6.45 times 10 to the minus 7. Okay? You want to try one on your own? You want to try this one on your own? This one's a little trickier. Why don't we just take a few minutes? See. Sometimes when we do these, I recommend numbering your equations so that if you have to manipulate them, it's easier to keep track of what's going on. So we want to get to here, given equations 1 and 2. So can you see what you need to do equations 1 and 2 to get to 3? Some of you got the right answer. So what did you do? Reverse the first one, and what about the second one? Let's reverse the first one. So I'm just going to say -1, right? That's my own little notation that I'm reversing the first one here. I'll just write for you, reverse. So we take number 1, we reverse it, so that's going to give us 2NO2, goes back and forth with N2O4, and that means that the Kc for that, let's just call that -1, just to notate that. So we've run it in reverse. So what's that new equilibrium constant going to be? It's the inverse, right? So it's 1 over 1.5 times 10 to the 6th. So that's going to be something times 10 to the minus 6th or 10 to the minus 7th. Let's see. 1.5 times 10 to the 6th inverse. 1, 2, 3, 4, 5, 6, 7. 6.7 times 10 to the minus 7th.
Okay? And then what do we do to reaction 2? Anything? No. So let's just keep number 2 the way it is. N2 plus 2 O2 is in equilibrium with 2 NO2. That K is just what we started with. That's going to be 1.4 times 10 to the minus 10th. And we know this because if we now add these up, we should get reaction 3. Let's see, does anything cancel out? Yes, 2NO2 cancels with 2NO2. And so we end up with N2 plus 2O2 is in equilibrium with N2O4, which is number 3. So now we know that to get to the new K sub 3, what we want, we're going to do what to these two that we just calculated? We multiply them. All right, that's all we need to do. So that's going to be 1.4 times 10 to the minus 10th times 6.7 times 10 to the minus 7th. And that's equal to, what did we say? 9? 9 times? 9.33. 9.3. I got something different. 9.4. Ooh, that's big different.
I didn't do any rounding, so
well, and maybe I rounded poorly. I don't need to plug it in my calculator. You're going to get about 9 point something times 10 to the minus 17. Okay. This is not a class in calculator, using your calculator. So, once again, always set it up and show very clearly what you're doing so that if you do mess up in your calculator, you won't get points off for that.
I'm not going to tell you what's involved. Just do the top part of this question. All right, I'm going to intervene simply because this problem should be a fast, easy one. And if you haven't gotten it yet, then I want to intervene to help you realize what it is you need to do. So what do you need to solve for this one? What are you asked for? You're asked a simple question. You're given information and you're asked in which direction will the reaction proceed to reach equilibrium. All right, so what are you going to do? Take a look at the reaction. Write the mass action expression. Now you need to make sure that you write the correct mass action expression. Now it's not just, it used to just be we do products divided by reactants. But then the last lecture, I warned you, sometimes you've got a heterogeneous equilibrium. And you're seeing some of those in the homework assignments now. To write equilibrium expressions when it's homogeneous, like this one, all right, it's all going to be the concentration of the products raised to the power of its stoichiometric coefficient, so that's NO squared, divided by the concentration of the reactants, N2 raised to the first power times O2 raised to the first power. Now, if this were a heterogeneous, if one of these was a solid, then now you know that that doesn't get included in the mass action expression. Or if it's a liquid, it doesn't get included. But if it's a gas or if it's something in aqueous solution, that's what we include. Okay? Make sure you're clear on that. Now, we're given at the instant when a reaction vessel contains these amounts. So that's your Q. All right? So let's pop those in. Q is equal to, now we have to just make sure we're careful here. I want NO. NO is 0.0042, and that's squared, divided by N2, which is 0.5 to the first power, and O2, which is 0.25 raised to the first power. That's what Q is. What do you get for Q? 1.4 times what?
Times 10 to the negative fourth.
Times 10 to the minus fourth. That's Q. Now, what else do we need to know to see if this reaction is going to proceed in the forward direction to equilibrium or the reverse direction?
KC.
Hmm?
KC.
KC or KEQ. And are we given that?
Yes.
Yeah, it's right here. Okay. Is Q greater than or less than KEQ? It's less than. Q is less than KEQ. So which way is it going to go? And if you can't remember, just write your little graph here. reactants, products. All right, here's KEQ. Q is less than KEQ, so it's going to go in the forward direction. All right, and that's all you need to do for a question like this. All right, so part of this is to recognize what you need to do when you read a problem. All right, because once you recognize it, the steps to solve it are just two quite straightforward steps. Write the mass action expression and then plug the numbers in. Okay? So now do the same thing. Here's your initial concentrations for a new reaction, okay, with a new equilibrium constant. Does that one go in the forward or the reverse direction when it's going to equilibrium? Yep. I just solved it on the slide in case you want to check your work. But I saw a lot of people who were nodding their heads when I did this, so I'm guessing I did it right. And hopefully you all did it right too. Okay. So now that's an example of a type of question where you don't need to solve every single bit of it from the very beginning to the very end. Let's see what you make of this one. Let me give you a little bit of help, just so you don't make any mistakes. To interpret this, you're starting with 2 atmospheres
Set it up like this.
of these and nothing of the product.
So the change is these are minus x and these are plus x. Yeah, since it's going that way, these
All right, are you ready for me to intervene? Okay, I don't want to leave you unknown for too long. Right? This one was more of a process. Right? You had to take it all the way through. This is a rice table. Now, I should say, for those of you who I walked around, and this isn't a negative, well, it sort of is, but if you're just now looking back through your notes to figure out, oh yeah, how do we solve a problem like this, okay? Ideally, you would already be familiar with the strategies and you wouldn't have to be looking back at your notes now to see, oh yeah, how is this one solved, all right? The hope was that through doing the homeworks and through reviewing your notes, you've been practicing these strategies so that when you see them, boom, you'll know how to do them, okay? So this is a rice table, right? We're given the reaction and we're given the initial. We need to calculate the change and then we calculate the equilibrium. And we know which direction this reaction is going to go to equilibrium because there's no products right now. So it's going to go towards the product side, which means we're going to lose some x here and we're going to lose the same amount of x there because these react in a 1-to-1 molar ratio. And the products are produced in a 1-to-1 molar ratio, which means that if we lose x from the reactants, we're going to gain x in the products. Now, if there were coefficients here, if there were a 2 here, then this would be 2x. Right? If there were a 3 here, then that would be 3x. Right? Now we can figure out what we'll have at equilibrium. This is going to be 2 minus x. This is going to be 2 minus x. This is x, and this is x. Now, at equilibrium, right, KEQ is equal to 10, which is going to be equal to the concentration of, let's just be thorough, H2 times the concentration of CO2 divided by the concentration of H2O divided by the concentration of CO. And now we have all those values algebraically. That's going to be x times x divided by 2 minus x times 2 minus x. All right, that's the same as x squared divided by 2 minus x squared. That's equal to 10. And we want to know what x is because we have to calculate what the equilibrium concentrations are. Now you might think, oh, I got to do a quadratic on this, but you don't because you recognize that, well, I've got a squared term in the numerator, a squared term in the denominator, so I can just take the square root of this whole thing. And that gives me x divided by 2 minus x equals 10. And now that's easy to solve. Yeah?
Square root of 10, right?
Square root of 10, thank you. Square root of 10, which is something a little bit greater than 3, because the square root of 9 is 3, so I'm guessing it's 3.2?
That's 3.16.
Oh, that rounds to 3.2, right? 3.16. You have a calculator, use it. All right? So now we have x is equal to 2 minus x times 3.16. X is equal to, what is that? That's going to be 6.32 minus 3.16x. Combined terms, 4.16x is equal to 6.32. See, I can do all that without a calculator, but now this step, x is equal to 6.32 divided by 4.16. Well, gosh, I almost don't need a calculator for that. 1.52, that's x. So now we know what the equilibrium concentrations are. 2 minus 1 point, let's just say 1.52 for the ease of getting through this one. So this is going to be 1.5. Well, let's just put them on 1.52, 1.52, and then 2 minus that is 0.48, and this is 0.48. Those should be the equilibrium concentrations. And how can we check our work? Plug them into, go ahead. Plug them into the mass action and see if we get something pretty darn close to 10. So what is 1.52 squared divided by 0.48 squared?
10.
Is it 10? Then we have done our work. Good. Check plus.